All right, so we're going to look at section 9.3, number 67, which is about Euler's constant. And the problem gives us that S sub n is the sum of k equals 1 to n of 1 over k. So we're adding 1 plus 1/2 plus dot 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 plus 1 over n. For part A, I'm going to let f of x, I'm going to look at a function, let f of x equal 1 over x. And f of x is positive and continuous. On 1 to infinity. Now S sub n, I'm just going to write out some terms. S sub n is f of 1 plus f of 2 plus f of 3 plus dot 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 plus f of n. And what I want to do is look at a graph of f of x equals 1 over x, and we're going to look at inscribed and circumscribed rectangles. So let me draw a little graph here. There's f of x equals 1 over x. And we're going to look at 1, 2, 3, and we're going to go to out to n, and we'll say n minus 1, n, and out to n plus 1. So I'm going to look at the circumscribed and inscribed rectangles. So I'm going to draw some rectangles here. And I'll do these, the circumscribed rectangles, like so. I'm going to go out here and do this. Need that in blue. There we go. The area of the inscribed rectangles, I'm going to say A sub I. Area of the inscribed rectangles is f of 2, our base width is 1, f of 2 plus f of 3 plus f of 4 plus dot 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 plus f of n. Well, this is just equal to s of n minus f of 1. And f of 1, in this case, because f of x is 1 over x, is s sub n minus 1. The area of the circumscribed rectangles. Area of the circumscribed rectangles is f of 1 plus f of 2 plus f of 3 plus dot 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 plus f of n. We have our last circumscribed rectangle there, which is just equal to s sub n. Well, s sub n minus 1 is less than or equal to the value of the integral of f of x equals 1 over x, from 1 to n, where the inscribed rectangles, the area of those rectangles are less than or equal to the integral. So that's going to be less than or equal to the integral from 1 to n of 1 over x dx. So, which is less than or equal to, let's do it this way, equals natural log of x evaluated on 1 to n, which is natural log of n minus natural log of 1, which is just equal to natural log of n. So that gives me the inequality s sub n minus 1 is less than or equal to the natural log of n, or s sub n is less than or equal to the natural log of n plus 1. And the area of the circumscribed rectangles is greater than or equal to the integral of f of x equals 1 over x from 1 to n plus 1, because our last circumscribed rectangle is out here past n to n plus 1. And I guess since I use small n's here, I'll change these to small n's here. There we go. So I'm going to switch pages, but we're going to do the same analysis with the area of the circumscribed rectangles. Area of the circumscribed rectangles is greater than or equal to the integral from 1 to n plus 1 of 1 over x dx. And the area of the circumscribed rectangles is s sub n. So we can say s sub n is greater than or equal to the integral from 1 to n plus 1 of 1 over x dx, which equals the natural log of x evaluated on 1 to n plus 1, which is equal to natural log n plus 1. And this gives us the inequality that the natural log, so let me write one more step, s of n is greater than or equal to the natural log of n plus 1. And we get the inequality, so if we combine this with the one we did on the previous page, we get the natural log of n plus 1 is less than or equal to s sub n, less than or equal to the natural log of n plus 1. And I can rearrange this, subtract natural log of n from everything, natural log of n plus 1 minus the natural log of n less than or equal to s sub n minus the natural log of n less than or equal to 1. Well, the natural log function is increasing. So ln natural log of n plus 1 minus the natural log of n is greater than or equal to 0. Natural log of n plus 1 is larger. And we can write the inequality then that 0 is less than or equal to s sub n minus the natural log of n, which is less than or equal to 1. And the first part was asking us to show that this thing is bounded. Oh, sorry, to establish this inequality. The next part asks us to show that the sequence is bounded. All right, so let's look at that. I'm going to change my pages here. All right, so for part B, we want to show that the sequence, all right, let me do this a little better. A sub n is the sequence S sub n minus natural log of n. Well, we have that 0 is less than or equal to S sub n minus natural log of n, less than or equal to 1, which shows that this sequence A sub n is bounded. So I guess I combined both of these. I combined parts A and part B in this first bit. For the first part, we were supposed to establish this first inequality, and for the second part, so I guess this would be what we do for A, and this would be what I needed for B. So part B, we showed this, so our sequence is bounded. Now we want to show that our sequence is monotonically decreasing. So this is for part C. For S sub n, to be monotonically decreasing, we need A sub n plus 1 to be less than or equal to A sub n. And I'm going to say this is true when A sub n, I'm going to subtract A sub n plus 1. That has to be greater than or equal to 0. So I subtract A sub n from both sides, I get this inequality. So I'm going to show this is true. A sub n minus A sub n plus 1 equals, from what we talked about before, S sub n minus a natural log of n minus S sub n plus 1 minus the natural log of n plus 1. I'm going to rearrange this a little bit. So this is S sub n minus S sub n plus 1 plus the natural log of n plus 1 minus the natural log of n. Well, this quantity, natural log of n plus 1 minus the natural log of n, is the integral from n to n plus 1 of 1 over x dx. And we're going to take a look at what this quantity is. S sub n, from what we wrote before, let me back up here. S sub n is f of 1 plus f of 2 plus f of 3 plus dot 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 plus f of n. S sub n plus 1 is the same sum, 1, f of 2, f of 3, dot dot dot, all the way to f of n plus 1. So S sub n minus S sub n plus 1 is f of n minus f of n plus 1. All of these other terms are going to subtract. Well, let's look at a little picture of the graph of f of x equals 1 over x. So here we are out here. Here's n, and here's n plus 1. F of n minus f of n plus 1, this area of this rectangle, this little rectangle, is 1 over n plus 1, because the difference between these is 1 unit. So the area of this little rectangle is 1 over n plus 1. Well, that is f of n minus f of n plus 1 is 1 over n plus 1. So f of n plus 1 minus f of n is 1 over n plus 1. So f of n minus f of n plus 1 is going to be negative 1 over n plus 1. So this quantity is negative 1 over n plus 1. So a sub n minus a sub n plus 1 is negative 1 over n plus 1, plus the integral from n to n plus 1 of 1 over x dx. Well, the integral from 1 over n, the integral of 1 over x dx from n to n plus 1 is the area of this entire region. And the area of the rectangle is 1 over n plus 1. So the integral of, so the area of the total area under the curve minus the area of this rectangle is going to be positive. And I'm going to say we see that a sub n minus a sub n plus 1 is greater than or equal to 0. And I'm going to write area of rectangle. So that shows that our sequence is monotonically decreasing. Well, if the sequence is bounded and monotonically decreasing, then our sequence converges. And we call the sum Euler's constant. So that's part D. And the last part wants us to approximate Euler's constant with a sub 100. Well, a sub 100, we decided that a sub n is s sub n minus the natural log of n. So that's going to be s of 100 minus the natural log of 100. And that would be approximately what Euler's constant would be. So that's going to be 1 plus 1/2 plus 1/3 plus dot 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 plus 1 over 100 minus the natural log of 100. And then there we've shown everything we wanted to show for number 67.